Alright, today we are tackling one of the most elegant, most baffling, and just downright beautiful experiments in the entire history of science. Seriously, this is an experiment so profound it didn't just change our understanding of light and matter, it completely shattered our concept of reality itself. So let's just start with a simple question. Imagine you've got a wall, and you cut two little parallel slits in it. Now, if you took a can of spray paint and sprayed it at the wall, what would you expect to see on the surface behind it? Two lines of paint, right? Of course, it's just common sense. So you'd think if we did the same thing with a beam of light, we'd get the same result. Two simple, bright lines. But that is not at all what happens. Not even close. Instead of two nice, neat lines, you get this, a whole series of bright and dark stripes spread out across the screen. And here's the really weird part. The brightest spot is right in the middle, exactly where you'd expect a shadow to be. This result makes absolutely no sense, and it's the central mystery we're going to unravel today. So what on earth is this pattern, and how does it even form? The answer forced scientists to throw out the rulebook and rethink everything they thought they knew about light. This crazy pattern is officially called an interference pattern, and for scientists back in the early 1800s, this was a massive headache. You see, the top theory of the day, championed by none other than Sir Isaac Newton, was that light was just a stream of tiny particles, like little bullets. But particles don't do this. You can't shoot two streams of particles and have them cancel each other out to create nothing. Something else had to be going on. The solution, it turned out, required a completely radical new idea. One that directly challenged the authority of Newton himself and suggested a totally different identity for light. So in 1801, this British genius named Thomas Young comes along and conducts his famous experiment. And his results gave powerful evidence for a competing theory. What if light wasn't a particle at all? What if it was a wave? Now this was a huge deal, going completely against established science, but it was the only idea that could explain that bizarre pattern of bright and dark stripes. And what's so cool is you can actually hear Young explaining it himself. He made an analogy to something everybody can understand: sound. You know how two sound waves can combine and get louder, or they can clash and cancel each other out into silence? Young basically said, hey, maybe light waves are doing that exact same thing. Okay, so this whole idea of waves cooperating or destroying each other, how does that actually work? Well, the answer is a phenomenon called superposition. Interference is just what happens when two or more waves overlap in the same space. They don't bounce off each other, they pass right through and combine. The height of the new wave, its amplitude, is simply the sum of the individual waves at that exact spot. And this simple addition can lead to two totally different results. So if the peak of one wave meets the peak of another, they're in step. They add together to make an even bigger peak. We call that constructive interference, and in our experiment, that's what creates a bright spot. But if a peak from one wave meets the valley or trough from another, they're out of step. They completely cancel each other out. Poof, nothing. And that's destructive interference, which creates the dark spots. And this image shows it perfectly. Think of it like ripples in a pond spreading out from each slit. The lines here are the crests of the waves. See where those lines cross over? That's constructive interference. That's a bright band. And in those empty spaces between them, that's where a crest is meeting a trough, and you get destructive interference, a dark band. The reason for this pattern comes down to what we call path difference. For any spot on that back screen, the wave from one slit has to travel a slightly different distance than the wave from the other one. Now, if that difference in distance is a whole number of wavelengths, the waves arrive perfectly in step and create a bright spot. But if the difference is exactly a half wavelength, they arrive out of step and cancel each other out into darkness. But to actually see this beautiful, steady pattern, you can't just use any old light sources. The conditions have to be just right. What we're trying to get is called sustained interference. That just means the pattern of bright and dark stripes doesn't flicker or dance around. It holds perfectly steady so we can actually study it. And to pull that off, you gotta follow a few rules. The single most important condition is that the light sources have to be coherent. It's a technical term, but all it means is that the waves coming from the two slits are marching perfectly in step with each other, maintaining a constant rhythm. This is actually why Young used a single slit to feed the double slits. It guaranteed the two new wave sources were perfectly coherent. It also helps a ton if the light is just a single color or monochromatic, because that's what gives you those really crisp, clear stripes. So the main takeaway here is that this isn't just some clever light trick. Young's experiment proved that light behaves like a wave, and that was a monumental discovery. But what nobody could have guessed is that a century later, this exact same experiment would break physics wide open. Because this is where the story gets much, much stranger. By the 20th century, we knew for a fact that things like electrons were particles. I mean, they had mass, you could bounce them off things, they were solid. But in 1961, a physicist named Claus Johnson asked a wild question. What if we shoot these solid little particles through the two slits? The result was world-changing. He got the exact same interference pattern. This discovery is so profound that a later version of the experiment was actually voted the most beautiful experiment in all of physics. You know what they did in that version? They fired one single electron at a time. Now just think about that for a second. If there's only one electron in the setup at any given moment, there's nothing for it to interfere with. So how in the world can it possibly form an interference pattern? The answer to that question forces us to accept a conclusion about reality that seems to defy all common sense. It turns out an electron isn't just a particle, it's also a wave. It is, fundamentally and simultaneously, both. This isn't a choice, it's just the nature of reality at the quantum level. That single electron leaves the gun as a particle, travels through the experiment as a probability wave that goes through both slits at the same time, interferes with itself, and then lands on the screen as a single particle again. It's absolutely mind-bending. This leaves us with a truly staggering final thought. The double-slit experiment reveals that the fundamental pieces of our world seem to exist in some ghostly state of all possibilities until we observe them. So, if a single particle isn't in a single place until we look at it, what does that really mean about the solid, definite reality we think we're living in every single day?